code. Okay, here we go. So, someone asked a question in the beginning of the sort of the pre-chat here on this stream, and they kind of wanted me to go back over where everything lives. They said like, where do structs live, and where do variables live, and stuff like that, and where do functions live. And the reason that I want to address that question specifically is because I am very glad someone asked. We have sort of said where these things live, but it's hard to kind of take a lot of this stuff in when I say it. And I really do want people to constantly be thinking about that, where things live. So I would like to mention again where everything lives. Code, which is like the things that we write here. Code lives first in the executable file. So when we compile everything and we get a .exe file, the code is in there. And the code is encoded. Code is encoded. The code is encoded in a format that is defined by Intel that basically says, well, and there's also defined by AMD now because I think they were the ones who officially did the x64 spec for 64-bit computing. But this code is being compiled for 32-bit computing. So defined by Intel, and encoding in binary that basically says what the instructions are that the CPU is supposed to do. So we have an executable, and the executable has that in it. And oh, wait, you know what? Do you guys think, I don't know if you're feeling this like I'm feeling this, but I think this could be a place where we could bring out the GIMP. I don't know, I don't know if you guys feel it. You know, I don't want to tell you how you're feeling, okay? I want you to be in touch with your own feelings, but I feel like this is a place where I could get out the Wacom drawing tablet. I got this little tablet, I've had it for a long time, and I could just go ahead and draw a diagram, right? Let's do that. Let's diagram this. Let's just go crazy. I don't know, this could be a big mistake, but like I said, Sunday stream, anything goes. I think you just have to say that. I mean, you know, people have standards, and standards are good, but sometimes you just got to go nuts. So let's see here. So let's see, can I get a smaller pen? How about oh God, what has happened? Yeah, my GIMP skills are not the best GIMP skills in the world. Let's see here. There we go. That seems reasonable. So basically what happens is we have all our code. Oh God, this is gonna be awful. Oh man, I'm gonna have to learn to use the GIMP better, or learn how to use the Wacom drawing tablet better, I guess. All right, let's see here. So we have code that we write, right? And the compiler and the linker, well, so the code goes into the compiler, right? The compiler spits out actually what's called an OBJ file, and we'll be looking at those in the mainstream a little bit. The OBJ files go into the linker, and they're joined with things called libs. And libs are basically a bunch of OBJs that have been compiled together into a group. So they're things like the system libraries and stuff that sort of allow us to interface with the system. These all go in to the linker. You know what, guys? This diagram's turning out awesome. Look at this. This is awesome. Tell me you don't love this diagram. This is amazing. I mean, look at it already. Look at the majesty. Anyway, so the code goes into the compiler, spits out an OBJ file, libs and OBJs go into the linker, and the linker spits out an executable, right? And that sits on disk. And this is in basically a Microsoft well, wow, that's good. Microsoft Intel format. And what that means is basically Microsoft, because it's Windows, defined the format of this executable, which is basically the layout on disk. And the layout involves stuff like, and this is not the actual layout of an exe because I don't even remember the actual layout of an exe. It's been years since I've looked at it. But it's basically something that's like, you know, a header that says this is an executable file, and this is the exe on disk. This is on disk, right? It's got like a fix-up table, right? So there's a thing in here which basically a bunch of data that says where we called system calls, like where we called all the stuff that needs to go to the operating system. And then it's got Intel format code, right? It's got the operands for the CPU, all the stuff. It's got all the CPU code that we actually generated all bound up in here, right? So then what's going to happen is, oh, and feel this. Are you ready for this? This is going to be insane. You're not ready for it. I know you're not, but dig it, right? Are you feeling that? Insane, right? You didn't think I could do it, but I did, right? All right, so what basically happens is, you know, you can go look this up. There, if you look up Windows executable or something on Wikipedia, you can go look up the actual structure of this if you're curious about it. because it's not that complicated. It's pretty straightforward. But basically what happens is Windows then comes along and it's like, in the shell you say, I want to run this executable, right? You're just like, I got to run this executable. So what it's going to do is it's going to load up this code, right? It's going to take this code and it's going to put this code into memory somewhere. So here's the memory now of the machine, right? And it's going to take the Intel code stuff and it's going to put it in here. Then what it's going to do is it's going to look at this fix-up table, which basically tells it a bunch of places in this code where we called system calls. Because remember, when I said in one of the streams, I'm like, we don't actually compile the whole thing together. There's always a little bit of linking left to be done, because any place we call a system call, well, the system, Windows, is outside of our executable. So we basically have to call Windows' executable code somehow, and how are we going to do that? We can't compile all of Windows into our thing, because then you'd have to start Windows with our code in it somehow, right? That doesn't make any sense. We'd have to write the operating system for that to be true. Wouldn't that be a nice world? By the way, that's how things used to work on like the Amiga and stuff. You used to actually have kind of, when you wrote a game, it would boot right into the game, or a C64 as well. But ignoring all that. So anyway, what happens is it goes in here, the OS goes in this fix-up table, basically, and I'm skipping a lot of kind of minutia, but basically it's going to read a fix-up table that says, here's the places they called system calls. So go right into the memory and patch over, like overwrite the sort of blank area that's talking about the system call with an actual pointer to Windows, right? Windows code. So you know what, and I'm going to draw this a little more sanely because this I can actually do a little bit more. So here's Windows code. Okay? And the question is, how does Windows code get there? This, if you remember, I talked about virtual memory and virtual address spaces, right? And I said that when you run your program, you get your own virtual address space. And I'm like, it's your own address space, it's all your own memory, and Windows behind the scenes is kind of mapping that memory to RAM. So this is our virtual address space, basically, and it doesn't necessarily correspond to the physical memory of the machine, it just maps it in and out as it's necessary, right? So what happens, actually, is that in your virtual memory space, Windows actually goes ahead and maps a copy of the stuff that you need to call into your virtual address space. So it takes it from its space, right? Here's the actual Windows code that's actually running in its own, address space and doing whatever it wants to do. And basically, it goes ahead and maps that into your address space. Then it patches up your code to point into that code. So anytime you called, like when we had our code, I don't know if it's still in there. I think it is. Yeah. So we had this output debug string call, right? And we needed to call Windows. That's what was going on. It was basically when the code was loaded, it was finding that call using the fix-up table that the linker output, and it was patching a call to the actual location of output debug string, which was somewhere in here, right? That's roughly how linking goes. When all of that fix-up is done, then it uses one final piece of information in, it's not really called, it wouldn't be called a fix-up, it wouldn't be in a fix-up table, quote unquote, but it would be the entry point, which is basically the location in this code to start running. And it just jumps right into that and then goes, right? That is how basically something gets running on an operating system. And like I said, I skipped a lot of minutia there, and every operating system has all kinds of crazy, wacky stuff that's going on that's probably a little different from this, but that is a reasonable conceptual model of what's happening when you actually do stuff. So when you ask where code lives, that is where code lives. It first lives in the executable in here. It then gets loaded into memory. And mind you, it can often be demand paged into memory, so it will be virtually mapped into memory, but it may not actually get copied into memory until you actually hit the part of the code that you actually need to run, at which case it'll load that in. This is starting to look like a John Madden kind of diagram, you know what I mean? Anyway, so basically what happens is that code lives in a space in memory that Windows allocated and Windows mapped it in. Now, again, since it's a Sunday stream, and we're just going all out in the Sunday stream, I mean, look, you came to the stream on Sunday. I get to do whatever I want on Sunday. Okay, that's just, we're making a new rule. I know we don't have rules on this stream yet, but it's like, that's just the way things are, okay? It's like, it's anything goes on a Sunday. Stuff just goes nuts. So basically what happens is, the virtual memory system, you'll remember I talked about pages, right? So if I have an address space, if I have a virtual memory address space, we'll call that a VMAS, virtual memory address space, right? And it starts at 0 and it goes up to like high number, very high number, many gigabytes of memory potentially, especially on 64-bit. On 32-bit, the highest number you can represent is 4 billion, so it can only go up to 4 billion. But in 64-bit, it can go up much higher than that because 64-bit is huge. Anyway, I have a virtual memory address space, and it's divided up into pages. These things are called pages. This is a page, this is a page, this is a page, right? And these pages are typically like 4,096 bytes, right? Or 64,000 bytes. Well, 65536, 64K, it's times 1024. These pages are usually sizes like that, so they're pretty granular, but they store a fair bit. 64K is a fair bit of data in there. There's a reasonable amount of stuff in there. So the virtual memory address space is divided up into pages, and those pages, there's basically like a table, right? There's going to be a table in the operating system that is I think it's usually called a page table. I don't really know what they call it in Windows, but anyway, there's usually a table, and what that table does is that table records like what's going on with these pages. It's like, okay, this page, is actually stored on disk somewhere because we paged it out. So this page is out in disk, so it's not actually in memory. There's no physical memory backing it. But this page right here, that is in physical memory. That's over here in the actual memory of the machine or something like this. And like I said, I don't know how they implemented this on Windows, so I'm not trying to tell you anything specific about how Windows works. I'm just saying conceptually it's going to kind of understand, the operating system knows where these things are. Now, the processor, the Intel processor, basically has ways, it has support for this in the hardware, where basically each page can have flags set on it. And those flags have to do with what can happen to that page. It's like, can you read this page? Can you write this page? Can you execute this page? Can you execute code, basically, in this page, right? And those flags are set on the page, so what Windows will do is it'll go, I am running low on physical memory at the moment. I need to make some space in the physical memory. And this page is like in the physical memory. So what I'll do is I'll grab what's in this page, I'll write it out to disk, and then I'm going to unset the read and write flags for this page or something like this, right? And the exec page. It's guarded. The page is now completely off. You can't do anything to it, right? What will then happen is when your code goes to do something on that page, whether it happens to be a code page, so it's going to try to execute code, and as it's executing through the instructions, it eventually gets into this page and tries to execute something, or if it's memory and you're trying to read from it or write to it, like you would, just variables are in there or whatever, and you're accessing them. What will happen is your process will just grind to an immediate halt, and you'll have what's called a page fault, right? You will basically cause a fault. There'll be an interrupt, and the operating system will wake back up, and the Intel processor basically gives the operating system the option to do something at that time. And what the operating system will do is it will go, oh, somebody needs this page now. Okay, I'll go back out to disk, I'll get it, I'll shove it back in here, and once it's loaded, I'll restart that process where it left off. So it basically freezes what you're doing, does the operation necessary to put it back in there, and then keeps going. So hopefully that makes some sense. And that's true of code pages as well as data pages and everything else. That's what a virtual memory system basically is. It's a system where the operating system wakes up anytime somebody needs a page that's not there and does something to make that work. Now, what can happen if the program's just bad, if the program's written wrong, and we'll have this happen during our stream, I'm sure, because it's easy to have bugs in your code, obviously, you might accidentally write to a page that's off limits. Like, for example, you never allocated anything in this page. This page is not even a thing. You just wrote to an address, some random address in memory. You tried to write to it, and you never even told the operating system something was there. Because all these pages, before the operating system is going to start tracking them, all the pages, they have to actually be known to the operating system. So you have to make calls to the operating system to say, I'm going to use memory in this page now, right? So what happens then is you get a page fault, and the operating system wakes up and goes, I don't know that page. What is that page? That doesn't make any sense. You're obviously messed up, and I'm going to stop you. And that's when you get that little box that's like, this system has caused an access violation, right? And you've all seen this. You've all been playing the game and had that happen, I guarantee you. If you've played PC games, you've had an access violation pop up, and you're like, wah, wah. Well, that's what happened. Basically, someone had a pointer pointing somewhere it shouldn't, they wrote into it, or God knows what, something bad happened, and off you went. Okay, so that's kind of a conceptual model for it, right? So basically, the first answer to where code and data and all that stuff lives is it lives in that virtual address space. And basically, that virtual address space is broken up into pages. So here are my pages, right? And each page is basically stored somewhere. It's either in the physical memory, right? So each page is either in there, or it's on disk somewhere, right? And so what will happen is, for efficiency's sake, when Windows goes to load your code, which is on disk, the executable, what it might choose to do, because there's no reason it can't, what it might choose to do is not ever actually load the code. It might just map the pages, right? It'll map these pages to the spot on the drive where your code actually is. Then it'll just start executing the code right in the memory that doesn't exist and let the page faulting bring the code actually in. It could decide to do that, right? And for efficiency, maybe that's a good idea, because now if there's code that you don't ever really execute very often, it never has to get loaded. Might not be a great idea for performance, because it means when you go to execute this piece of code the first time, it's like, oh, we hit, we got to go page out to disk, et cetera, et cetera. So the smarter thing would probably be to start this loading all the pages, but you could start executing beforehand, and that way if the disk didn't beat the code to the execution, it could do blah, blah, blah. There's all sorts of stuff here. It's good. It's all good. Anyway, that is some fun diagramming of where the code lives. So I'm going to rearrange this here. Now let's talk about where everything else lives. So functions, they all live in there. They all live in the executable, then they get paged into the memory as they need to get executed, and the CPU pulls them in to execute them. Now, since we're being banana cakes, there's one more thing you should be aware of. Here's the CPU. This is my x86. It's actually an x64 in this machine, but it has it has the ability to execute x86 code. So typically in a CPU, we've got code here, and I said it was in the Intel encoded format, right? And I actually showed you this encoding, right? If you remember, I showed it to you. We did something where I went in here and I did I don't know, something. I don't know what we were doing. Who knows what we were doing at the time. But I went in here and I did go to disassembly. And there was this button here, is show code bytes, right? And I did show code bytes on and off. And basically what happened there was I just turned on the ability to see what the actual encoding was for these instructions. So this is what's actually stored in the executable and what's actually going to run on disk, what's actually going to run in memory when it's loaded. This is the actual encoding. That's what's stored. It's these bytes right here, right? Here's the location in memory where the byte is stored, and here's the bytes. And this is each instruction. So here's a function call, and the function call is encoded this way, right? So that stuff is in memory somewhere. So it got loaded into memory, and the CPU is trying to access it. So the CPU comes and grabs it as it needs to. So as it's executing instructions, it's going to the next instruction. The next instruction hasn't been loaded yet. It goes off to get it. And what happens is it brings it into the CPU, but not necessarily directly. There's a thing typically called an iCache, right? And that's called an iCache, I believe, because it stands for instruction cache. And basically what happens is the CPU may not want to directly execute stuff out of memory, because that stuff may need to be sort of further munged for the CPU to use it. It may need to expand some things. It may need to microcode certain things. I mean, who knows what it does. Like I said, not a hardware designer. I'm not going to try and pretend I know exactly why they have all these things. But point being, it becomes more efficient for the CPU to basically cache the instructions that it executes in its cache, in its local cache on the CPU, so that it can quickly access code that it's running. So for example, if you have a loop, and that loop's going to execute tons of times or something, so you're running all this code, it wants to do a bunch of work on that code first, and then be able to just execute that code straight out of its cache instead of going to memory every time to kind of pull it back in. So there is this thing called an iCache, and it does exist on most CPUs now, that basically preps the code for use by the CPU in some way that the CPU understands, and it's used as a local sort of way of storing that code. Now, you may think that's complete minutia, that's uninteresting, and you never need to know it. I have actually seen times on projects where the iCache was the problem. I think I even may have created an iCache problem one time. I think on Bink 2 I did a bunch of stuff with code generation that later on a certain platform, Fabian ended up having to optimize by just making the code smaller, because the iCache was actually a penalty. Like filling the iCache was actually a problem. Don't quote me on that. Ask Fabian about it. But anyway, so that's basically what happens with code. Now with data, right, you'll remember, so I've got these pages, right? We keep going back to this pages thing, but I have pages, pages, pages. So here's my virtual memory address space, and I've got all these pages in there. Well, what happens when I start executing my code right? And you look back here and you got, we came into WinMain. So we were in WinMain having a good old time. And I try to declare this local variable. It's a projectile, right? It's this big, it's a 16-byte structure or something that we've got here, right? It's this thing I want to declare. And I talked about the fact that it goes on the stack. Well, what is the stack? And I sort of showed, I showed how you could go look at where the memory was and that sort of stuff. But I also said that someone has to allocate everything. And so the person who was doing that was actually the startup code. I think it's actually the startup code in Windows that sets up the stack for you. I'm pretty sure. Think about it. I'm pretty sure that's true. Not the C runtime library, because I've compiled without the C runtime library and didn't have to set up the stack myself. So I think Windows actually sets up the stack for you. And what the stack is it's basically, it maps a page and it basically says, okay, this first page here at some address for this particular thread of execution of your code is going to be this page. And what I'm going to do is I'm going to set a guard page right after that page that basically says as soon as somebody tries to write into this page, right, as soon as someone gets to this page is protected so that it will cause a fault that will actually allow me to go map a new page in here. So there's basically a bunch of memory that's reserved for us to keep growing this thing down further and further. So the stack can just get bigger and bigger and bigger. And so that every time we call a function, it gets bigger, growing the stack. And then whenever we return from a function, it kind of moves the other direction. So stacks grow, they get bigger, and then they shrink, and then they grow, and then they shrink, and then they grow. And I talked about that procedure. But basically what's happening there is Windows is mapping memory for us to use as a stack, and when we grow out of the size of memory that we needed for our local variables and stuff, as we call deeper down into the functions of our program, it's just basically allocating pages on demand as we need them. And then when we come back through it, we are just using less of the stack. So there's it's basically like a water level that rises and flows. And like I said, the reason that it can do that is because there's never a need in a program to free something out of the middle of the stack. It never has to free some middle page here, right? It doesn't have to do that. It's always going to free off the back because functions nest, right? I call a function, I've got a function foo, right? It calls bar, and then that function calls blah, right? So I've got 3 functions here. Well, the top function, all of its local variables are going to have to stay in memory while bar is executing, and all of its are going to have to stay in memory while blah is executing. So until it returns back here, right, you can't just free the local variables of bar just right out the middle, because you're going to return from blah to bar, it's going to access the local variables, and all hell would break loose, right? So the stack always grows and shrinks from the top of it. It goes bigger, smaller, bigger. It never has to free out the middle. So it is not what is called a heap, which is something that can be freed out of the middle. It is not that. We will talk about that later. It is a stack, and it is a very clean data structure that lets you implement that cleanly. So all the rest of the stuff we talked about so far lives on there. Everything else lives on there. That's where it lives. So all this other stuff, projectile stack, test, everything, all of the functions all of the stuff that's passed to our function also either lives on the stack or is passed directly in CPU registers. That's just how that works. So hopefully that's a pretty complete answer to where everything lives, or at least has you thinking about the complete answer, and you can go research a couple of those things if you'd like to find out more about them. Okay. Good deal. So off we go, and let's take a look at the Twitch chat quickly just to make sure everything's going fine. It looks good to me. Everyone is talking amongst themselves. That is good. Okay. So what I wanted to cover today, and this is going to be a long stream because we went on a long diversion, and we may go on other ones. Like I said, Sunday stream is out of control. It's fully bananas. I wanted to talk about operators today. So what I wanted to do is kind of talk to you about the stuff that you can do once you actually have variables and stuff like we were declaring, and you understand where they are, but now you want to kind of do some interesting things with them. Which obviously, if you're making code, the whole point of it is to do interesting things with the memory that you've allocated. So I'm going to talk about operators today, and I'm just going to sort of spam some operators out there, and then we're going to talk about how they work. So first of all, there's obviously, if I have things like this, where I've got a bunch of variables that I've defined, and we all know how these work now. They go on the stack, so these are all living on the stack, and I want to start operating on them to do stuff. I have basically all of the math operators that I would normally expect to find, minus a few, perhaps, can be represented directly in C with operators. So I can basically say something like, okay, I want to make x now equal to y plus z, right? I can do that. I could say that I want to be y plus z plus x, and again, equals is not like mathematical equals. It's an assignment operator, which means it computes this side first, and then it assigns it to this side. Again, that caused me no end of consternation since I learned programming before I learned math. And when they started using equals to mean that both sides were equivalent, I had no idea what was going on. It was horrible. But hopefully you guys all can remember that difference easily enough. The equals in C always means assign. So it takes the right-hand side, called an RHS, right-hand side, and assigns it to the left-hand side, LHS, and it does that assignment. So after this statement is done, it equals these things. And we can use all kinds of operators here. We can do this kind of thing. We can divide, which is a slash. So it uses slash because there is no convenient way to make sort of a like an actual visual like thing over another thing like you would see in real math notation. So they just use the slash to sort of make it look a little bit like y is over z. We can do that sort of thing. We can also do minus, obviously. We can also do what's called a unary minus, which means we can put a minus before something and it makes it negative, just like it would in math. So you can type most mathy sorts of things in here. Things that you can't do is power of. So for example, if I wanted to say x to the second power, that is not what that would mean, because that is not an operation that was built into C. Instead, you have to call a function to do that. There is a function called pow, which we'll cover maybe later, that's in the C runtime library if you wanted to do that. But yeah, that's a separate issue. So you can put most math operators in there, and they work how you would expect. Star is times instead of x, because x would be a variable name. So they use star for times, just like most computer things, and they use slash for divide. Now, the thing that you want to remember is that much like in mathematics, in C, operators have what's called a precedence, which means that some operators happen before other operators. Now, this is exactly like how you think of them in math, really. I'm not going to belabor that point at all or even show a demo of it. I'm simply going to say it works very much like you would expect. Multiplication binds first. So if I say x times z, and then I have a plus on either side of it, no matter what it's doing, the x times z will happen before the plus happens. So the z plus x will not magically happen and then times z. It will do the x times z first, replace that with the quantity, and then continue to compute the pluses. So much like math, you do exactly that sort of precedence order evaluation. So divides and times will happen first, just like they do in math. Adds and subtracts will happen second, that sort of thing. It's not super important to remember the exact precedence rules, because actually the best thing to do is, if you're ever unsure about them, is just like in math, use parentheses. So if you wanted z plus x to happen first, put it in parentheses. And you can always do that just like you can in math. Now, the thing you can't do in math is infer a multiplication where there wasn't one. So I can't write that. If I wanted z plus x times z, I cannot write that. It is not allowed in C. You must always actually specify the operator. In mathematics, you can just put something next to something else and it means times. Not the case here. Same thing, I could not just use a space to say x times z. Can't do that. You have to always actually say what it is you actually wanted to do. Now you'll notice that I've used spacing here to creatively kind of show you what the operator precedence might be. And I find that that's a good thing to do. I find that it's usually a pretty good thing to do to leave spaces between pluses sometimes to kind of space out the equations and let it be clear to the person reading the code what happens in what order, or at the very least, what order you thought they were happening in. Because hey, maybe you had a bug in that code. It would be nice at least to see what the person thought they were doing, and then you go, oops, that's not going to work. For example, if I came into some code and I saw it looking like this, I might be like, oh, that guy didn't realize what's going to happen, because z times x will actually happen first, but it's pretty clear he thought that this was going to happen, right? And so, all of this stuff, like I said, it kind of comes with practice. It's not very complicated. It's pretty easy to understand. I'm not going to spend a lot of time talking about that. I just want you to be aware of the fact that all of the stuff that's at play in math is also at play in C, including operator precedence, and it's good to kind of get yourself familiar with it. It's really easy to look up if you want the exact rules and want to get yourself a little more familiar with them, but that is basically how that works. So, moving on to some things that are not going to be familiar to you from math. Those are mathematical operators, but there are also binary, like bitwise operators, because since we are working with memory, we sometimes want to do things that just have to do with the actual bits that are actually in the variables that we were talking about. And so if you remember, we did a thing where we learned hexadecimal, and I said that one of the big reasons why you use hexadecimal, like in fact one of the only reasons really that I ever use hexadecimal, is because it lines up with binary. So it's every digit, if you will, in a hexadecimal number corresponds to 4 bits, which means that you can easily see how the number breaks down that you couldn't if you looked at decimal, because any given thing, any given digit in a decimal number doesn't line up with binary at all. They're all mixed together. So you look at the number, you're like, I have no idea, right? If I see 65536, I can't break that at the 6 and say, oh, that was the bottom bit, or that was the bottom 3 bits or something. That's not, you can't do that. So I'm going to start to use hexadecimal here, which means you're all going to have to put on your hexadecimal hat to sort of show you a little bit more how this works. So let's say I make something equal to OXA, right? And now if you remember, A is the first letter after the digits in hexadecimal. So 0 through 9, and then A. So that's 10, right? We're all on board with that. In fact, we can just go verify that, right? We can look in here in the watch window, and I hit there, and I get my 10, right? And then I can see my hexadecimal. There it is. It's 32-bit number because I said it was an int, and there's the A, right? Well, what happens if I want to start sliding the A around? Sounds like a weird thing to do, but I want to, basically I want to move bits left or right in the variable. I just want to shift them around. Well, there is a shift operator, right? And what the shift operator does is it basically says, I want you to shift the bits either to the left or the right in this number by a certain amount that I tell you, right? So I want to shift the bits by, say, 4, which would be 1 hexadecimal digit, right? It'll move them 1 place to the left. So I go in here, and I have my number, right? It's A, like we said. I'm going to shift it by 4, and boom, the A moved, right to the thing. Now, what if I want to do that a few more times, right? What if I shift it some more? We'll just shift it. Just keep on shifting it by 4, right? So we'll watch it go. There's the A, right? Goes, shifts. Now the question is, what happens when I shift it and it's already at the end? Now the answer to this is actually that it's just C's defined behavior, what actually happens when you shift this, because in hardware there's actually a lot of different answers. There are things called barrel shifters, which actually can do kind of different things, like, for example, they can do what's called a rotate, where it comes back on the other side. So if I were to shift out the left side, it comes back on the other side, right? There's things which do shift to carry, which basically shifts out and replaces what you shifted out with zeros, but it sets a special flag on the processor that tells you whether or not there were any ones that got shifted out and stuff like that. So there's a lot of different things, but what happens in C, and somewhat unfortunately, because it's a bit limiting that it only has this one way, what happens in C is it just clears. If I shift bits out, it just goes to 0. The bits that get shifted out, they don't come back in anywhere. And so that's just how that works. And you can keep on shifting and they ain't never going to come back in again. They're gone. Goodbye. And even if I tried to shift back in, like, they don't go out to the next value in memory. It's entirely just in that one value. So you can never get them back again. But I can certainly intermix my shifts, obviously, with shifts in the other direction, right? You can shift by putting in the opposite version. So I did 2 less than symbols is the shift left. 2 greater than symbols is the shift right. And you can see now I can kind of do those shifts. Shift. You can see it wiggle back and forth. Shifting back. Now let's shift it up a few times and then shift it back down. And the same thing would happen if I shifted out the bottom. It would get cleared with zeros as well. So that's shifting. And you may think that shifting isn't particularly interesting yet, but you will see us do it a fair bit. There's a number of reasons why we might do it. I won't try to demo them today because we've been sort of just trying to cover the low-level stuff, and I won't try to get into the reasons why you might use it. But suffice to say, it's more useful than you might think, and you will see us use it in the mainstream. Furthermore, in addition to the shifting, excuse me, I gotta get another milk kit here. It's delicious. Anyway, so in addition to the shifting, when we're shifting these things, shifting these things all over the place, you may ask, well, what does that actually do with the number? Well, if you are a superstar, which maybe some of you out there are, and you only just learned binary and hexadecimal and stuff like that from this stream, but somehow you have a gigantic brain, and you think about what happens when you shift it. Now, what I said was every time we shift something, it basically moves the bits down in the direction that we shifted it. So if I have, say, 1 bit set at the very bottom, so I've got a number, right, and it's like 000, 000, 000. Let's say it's an unsigned char, so it's only 8 bits long. I've got 1 bit at the bottom, 1 little bit there. What does that represent? Well, we know that a 1 in that place represents a 1, and we know that a bit in the next place would be a 2, and then a 4, and then an 8, right, and then 16, and so on. So if I'm to shift this bit upward, so if I go ahead and shift that to the left once, what does that do to the number? Well, it was 1, now it's 2. If I shift it up again, now it's 4. And what I hope you can see is basically all that's doing is it's essentially moving up in the powers of 2 what the number was. So essentially when you shift by 1 to the left, you are multiplying by 2. When you shift to the right by 1, you are dividing by 2. So a shift is really just a multiply or divide by the power of 2 that you specified. So if I specify a 1, it's by 2, right? It's I multiply by 2, or if I was going the other way, that's a divide by 2, right? But if I specified a 2, well, that would be shifting 2 places, which is multiplying by what? 4, right? Because I had something here, and it went right to there in one shift. So that was multiplying by 4, not 2, which is 2 to the second, right? Same thing would happen if I shifted by 3. I'd start with 1, but I'd get 8, which is 2 to the third. So that is a shift by 3. So all you're doing when you shift is just multiplying by a power of 2, and the power of 2 is in this place. Make sense? Hopefully it does. Okay, on to more fun things. Although, actually, let's watch it. Let's watch it happen, ladies and gentlemen. We are in an IDE for a reason. Let us see in action. Show, don't tell is the way things go here on Handmade Hero. Oh. Probably gotta not have this bunch of numbers in the middle of the supposedly valid code. Okay, we're gonna switch out of hexadecimal mode. There you go, you got 10. So if we shift it up, what do we expect to get? 20. There's our 20. Shift it up again, we would expect to get 40. Got it. 80, etc. Right? Just multiplying by 2 each individual time. That's all that happens. And that's just it sliding up the hexadecimal. Now if we watched it happen in the hexadecimal like we did before, it's still the same, right? Just sliding up the thing, and so on and so forth. Anyway, oh, well no it's not. We changed it to 1 now, right? So we're not going by 4, we're going by 1 bit. So you can actually see the hexadecimal change as well. So it takes 4 steps to go up, which is kind of cool, right? You can watch it go. It's at A, right? Now it's 14, 28, 50, and now it's going to be back to A again as it slides in to 1 hexadecimal digit over. Computers are great. Really? You know? How do you not just love them? Anyway, so that's basically what happens with shifting, which is one of our bitwise operators. We have other bitwise operators. I'm going to set x equals to 0, and I'm going to show you some other operators. I'm going to use the shift that I just showed you to demonstrate these operators. And so here we go. I'm going to say shifted up by 4 for that one. I am going to say shifted up by, let's say, 8 for this one. Then I'm going to, again, use a shift by 4. And then I am going to use a shift by 8. You know what? We're not going to do that one yet. I'm going to do that one in a second pass because you know what? That one gets a little bit more fun, and I want to savor that one. So let's do that. Okay, here we go. So what I have done is I have written 2 more bitwise operators, OR and AND. And this is the sort of pipe symbol, if you're familiar with that. It's the vertical bar on your keyboard is how you do OR, and the ampersand is how you do AND. So I initialized x to 0, and you can see it here. right? And then what I'm going to do, oh, you know what? And is there any way to make this be binary? Can I just see binary? Does anyone know if that's possible? I would love to be able to just show you the binary here instead of the hexadecimal, because it would be so much nicer. Is there some way that I can just say Visual Studio Watch Window binary? Does it happen? I don't know. More Stack Exchange. Code Guru. Using the watch window. Does this actually have binary in it? Of course it doesn't. Google, why do you do this? Binary. Stack Exchange. Oh, come on, people. I'm not getting any satisfaction here. All right. Ladies and gentlemen, how you implement a debugger that doesn't have an obvious way to show you binary, I have no idea, but that is the way it goes. I suspect there's some kind of comma syntax maybe that I could do, but I don't actually know. So we'll try one more time. Again, Sunday stream, we're allowed to be meandering. I never have to do this anymore because I'm used to doing the hexadecimal, but like I feel like for educational purposes, come on, people, like wouldn't you have that in there? And even for like people who are not so familiar with it, I don't know. It just seems like the thing you would have. Let's say watch window, comma, syntax, Visual Studio, and roll the dice. Can you say, let's see, D and H for hexadecimal? Maybe they, isn't there like, you know, how to watch an expression in the debugger? Come on, MSDN, hook us up here. This is a high quality stream, and we want your help. Let's see. Most valid language expressions, used context operators, access control, ambiguous elements, races, inherent constructors, numeric constants. Okay. Can we do it? No, we can't. You can prefix or suffix symbols to represent numbers in another base, but it looks like you can't actually do it. Stream, am I right? Let's see. Printf%b int value. You can just use program mode in calc. Yeah, I know I can use calc. I want it in the actual debugger though. It's not looking good. Even the stream. If the stream doesn't know, you probably can't do it. So all right. We'll have to just do it the translation ourselves. But anyway, so what we're going to do here is we're going to try and look at this. Just using it in. Well, you know what? Here's what I'll do. Since in fact, I already kind of did it. I aligned them with hexadecimal digits, so we should just see ones appear, almost as if it was binary, because I aligned them that way to begin with. So this will be as good as we're going to get, I guess. What the OR operator does, which is the first operator I want to show you, is it basically sets bits in the value if either of its two operands happen to have that bit set. It's saying set the bits if either of the two inputs are true. So I have x, which is 0, so no bits are set in x. And I have 1 shifted up 4, which means there's a 1 in the 4th bit of this one. So when I OR these two together, I should just get that 1 bit set, which is the 1 shifted up 4. And I step and see, there it is, right? So it's OR, the two of them. Now what I'm going to do is I'm going to OR again with 1 shifted up 8. So that's a 1 in this place. So I'm going to OR these two together. And so what I'm going to do is it will keep the x, which is set, it'll keep that bit set, and it'll set the next bit as well, right? And now you can see there's two 1s, they both got set. So OR basically is just combines all of the set bits. Any bit that is set in either of its two operands, it sets in the result. So it's a way of combining things together. It's an OR. This or this. Now AND does sort of I don't know what the correct set theory term is for the operation, the inverse, the contrapositive, the whatever. It basically does a similar operation, but instead of setting the result when either of its operands have a bit set, it requires both of them to have that bit set. So I've got this coming in as x, 2 bit set here, but the thing I'm ANDing it with only has this 1 bit set, the 4 bit set. So when I AND them together, it essentially clears out that other bit that we set, the 1 shifted up by 8. That one gets knocked out by the AND. So AND is often used to do what's called masking, which is to say I have some bit pattern and I want to remove all the other bits from some value and just leave the ones that were set in these positions, right? So you could imagine me doing something like that, where I said, okay, I've got some value that is full banana cakes, right? Let's say I set a bunch of bits in here, okay? So I set the 3-bit, I set the 14-bit, I set the 19-bit, I set the 23rd bit, I set the 30th bit, I set the 1st bit, and I still set the 8-bit. So I just set a ton of bits, right? But now I want to know, I just want to see basically what bit, whether the bits were set in the 4th position or the 3rd position. Those are the only bits I want. Well, let's make it a little bit. Or the 30th. I want to see if either of those 2 bits were set, right? Let's make it even easier. 31st bit. All right. And so I'll assign those to a separate variable so we can look at them ahead of time. So that's our mask, basically. Our mask is the 4th bit and the 31st bit are set in Y. And then we've set all these other ones, 4, 3, 14, 19, 23, 31, 8. And now we just want to see what bits they have set in common. That is what the AND operator will do for us. So we go in here, we'll look at X, we'll look at Y, and we go through set bits, setting bits, setting bits, look at them all fill in. They're all filling in. Our X is full of bits, ladies and gentlemen. And now we're going to set our mask, which is Y. And the Y only has 2 bits set. It's got that top bit, the 31st bit set, the very last bit in the value, and it's got the 4th bit set, so that one right there. And now we AND them together, and bam, right? We get back just that 4-bit, because that was the only bit that they had in common. You can see that. There's the 4-bit, there's the 4-bit, and this 31st bit never appeared in here. It was never set. So it isn't set in the result, right? So that is basically what we mean when programmers say we're masking, when we mask out a value, because you sort of have a mask, like you would put on your face, that only shows a little bit through, right? Does that make sense? Hopefully that's clear what's happening there. OR and AND are the very most frequently used bitwise operators in C, at least when I'm programming. Those are the ones I use most often. But there is another bitwise operator. A bitwise, yeah, well, there's 2 more actually. We'll show you what they are. So one more bitwise operator that's fairly easy to understand is the not operator, basically. Bitwise not. It's a little tilde. It's kind of like when you put a negative in front of something. It changes the value of that something in the expression. Tilde in front of something means take all the bits that were 0 and turn them into 1 and turn all the 1s into 0s. It inverts the value, right? So basically, if I run in here, hello? What did I say? Oh, I had a warning. What was my warning? Just that something isn't used. I like to be aware when I have warnings. Yeah, just unreferenced variables. That's fine. I don't care if I have unreferenced variables. All right. So I got nothing set in X. I do the inversion operator, the not operator, and all the bits are now set. Every last thing is set. It's the maximum possible thing, right? And that is basically works no matter what you do. So if I make X be some combination of bits, right? I do, let's say, a couple bits set here. Right? Oops. This has to be an OR, ladies and gentlemen. So I go in here and I set some bits. I now have some bits set. I do the inversion, and it gives me exactly the opposite. Everything that was set is now not set. Everything that is isn't. And now someone brought this up in the chat. It's a good thing to remember too if you're struggling with these a little bit. It is true that if you load calc, right? So if you go in here and you just type calc, you'll get this calculator thing. Basically, that's built into Windows. Inside there's a view that can turn to programmer mode. And there's these things that you can set: hexadecimal, decimal, octal, binary, right? So if you set it to hexadecimal, I believe this will work. You can cut and paste just not the OX part, but just the part that you want to see. You can paste that in there, and then it will show you the binary down here, right? You can sort of see 1 1 1 1 0 1 1 1 1 0 1 1 1, right? And you can see that it's the inverse, the exact inverse. So you don't have to translate that in your head. You can do it here. You'd want it to do that in the debugger. That's where it should be. But for the, it's the poor man's way of having a debugger that actually works at all. Okay. All right, so there you go. So that is the not operator, the binary not. And basically it turns bits to what they are not, hence the name. But there's one more operator, and this one is a doozy. I do not expect people to understand this one right away because it's just a little confusing. It is no different than or and. It's exactly the same conceptually, but it's just a little bit harder for people to get because or and are very logical. It's like, is this or this set? And is like, is this and this set? It's very easy to kind of understand what those do. It's called exclusive or. And what exclusive or does is exclusive or if I have two variables. So let's say I have this, where I've got 1 shifted up 4, and I've got y is 1 shifted up 8, right? And what I want to do is I want to do exclusive or of these two values. In fact, let's make this a little bit more interesting by setting just a few more bits. There we go. All right. Okay, so I've got some bits set now. You can see I've got 2 bits set in X and 2 bits set in Y, and only one of the bits lines up. So if we were to do an AND on this, right, we would expect to just get the 8-bit, because both of them have 8. So the things that they both have in common, we expect them to get. If we were to do an OR, we would expect them to have all of these, right? The result would have the 4-bit set, the 8-bit set, and the 16-bit set, right? Well, what exclusive OR does is it does something similar to the OR operation, meaning that if either of the bits is set, the result will have it set. But if both of the bits are set, then it won't be. So it's exactly the same as an OR, except for the one case, which is when both bits are set, and that goes to 0. So the reason it's called exclusive OR is because it's set to OR, it's exclusively an OR. It excludes the case where they're both set. It's only the OR case. It's never the AND case. You can't do it when they're AND. You could only do it when they're OR, and that's exclusive OR. So when I run this, what do we expect to see, right? We expect to see that 8 get cleared out, right? And it is. So the result has the bit set where each of them had a bit set but the other one didn't, but the one where they both had it set got cleared. And I realize that's just a weird thing to think of conceptually, but it is something that happens in programming. It's just another tool you can use to achieve results that you want. So it's something to be aware of, and it is built into the language. Now, the thing that's interesting about XOR is that it's kind of symmetric in a weird way. So for example, if I was to do this twice, I'll show you some things here. So let's say I XOR something where I'm XORing X with Y, right? So I get the thing that I said before, it cleared out that bit. But now I XOR X with Y again. And what you'll notice is I got X back. So one of the most common things that XOR is used to do is in things where you want to be able to invert what you did. Because it's an operation that inverts properly. If I XOR something with something and then XOR it again with the same thing, I get the original value back. Things like cryptography tend to use this because you can XOR values together in ways that are invertible. In fact, really bad cryptography is basically just XORing things with some key, right? It's just like I XOR the data that I'm trying to quote unquote encrypt with some key, and then when I want to decrypt it, I just XOR it with the same key again. And I believe like it was Microsoft Excel, its encrypted file format for a while in the old days was just XOR. It was like we XORed with something. The times have changed. We don't do that anymore, but that was something. Anyway, so that's XOR, and that pretty much wraps up the bitwise operators that I wanted to cover. So that, again, you have OR, you have AND, you have exclusive OR, and you have NOT. And between those, you can do quite a bit of damage, ladies and gentlemen. That's quite a lot of bitwise operators you can do. And we'll be seeing those in the stream. You will not have to wait long to see me use those, I suspect. So you will get to see how those are in action, basically. Anyway, so let's move on to some other operators. They're, in addition to bitwise logical operators, they're called logical because they're like or and, like it's like kind of like logic, doing logic circuitry, right? There are what are called straightforward logical operators. I think they're just called regular logical operators. So there's bitwise operators and logical operators, I think, are the typical ways they're called. One of the problems with teaching a C class after you've known C for, I don't even know when I learned it, but multiple decades, is you forget the proper names for a lot of things. Because it's like, I don't know, it's just the thing that I use. I've never been a particularly highfalutin programmer who reads like, Lambda the ultimate or something. So I'm not the kind of guy who's like all about the nomenclature. And it's like, what? You don't know that's the set theory, the third way of representing the logical set theory operation of closure, division ring divided by the thing produces stuff? And it's like, no, I don't. I have absolutely no idea. I would love to know, but I don't know. Anyway, so there's also operators you can use that deal with whether values are 0 or not. And I wanted to cover these first because I was going to talk about conditionals. And conditionals are things basically where you can change what code is executed based on the values of things. And that is obviously a very fundamental thing that you have to do in programming. It is how the basis of all control flow, which is the thing we're going to look at next. But in order to understand how any of that works, you have to first be able to compute something you can use for control flow. And that is where these logical operators come in. So if I have a value, I'm going to talk about this. I've defined 3 things here. And what I want you to think about is each of these things. In fact, you know what? I'm going to get totally wild here, just full on, even though I haven't talked about 2's complement or anything. I'm going to define 4 things, and one is going to be negative. How do you like that? That's right. I did it. I put a negative in there. So I defined 4 things, and what I want you to think about right now is what each of these has as a Boolean value, meaning I'm going to talk about a Boolean value, which means is something true or false. I need to bake things down into whether something is basically true or false, on or off, let's say, is it set or not, whatever, however you want to look at it. But it's basically, I'm going to boil things down into 2 categories, and only 2. And the way that C makes this distinction for variables, and we'll see kind of why it does this in a second, but the way that it makes this distinction is by saying if something is 0, it is false. It is not true. It is not set. It is whatever, however you want to look at it. It is the not thing. And if something is 1, then it is true, right? It is set. It has a value. It is a thing. So, what C defines are a set of operators that can produce these things for you as well, that can use this sort of thing. And this trueness happens for anything that is not 0. It doesn't matter if the number is negative. It doesn't matter if the number is huge. It simply matters that it is not 0. So basically what happens is in C, things are either 0 or they are not. And that is how it thinks about Booleanness. So when we get into things like if statements and conditionals, those sorts of things, that is really the property of an if, of a true or a false. Is it 0 or is it not 0? So C gives you operators that can produce these values out of things that you want. So for example, I may want to know, let's say I'm going to call I'll do less. Say we'll do less than. X is less than Y, right? I'm going to compute that. X is greater than Y. X is equal to Y, okay? And I'm going to put these in parentheses because I like to be very clear about sort of how things are computed order-wise. Not equal to Y. So now we've got a bunch of comparisons here, and we will see how they work. Okay, so obviously between X and Y, X is 0, Y is 1, right? So if I start comparing these values, if I compare them to each other, what C will do is it will do exactly what you would have done in math. It'll do the mathematical comparison, greater than thing. This is how they do equals to, not so that you don't confuse it with assignment. They put 2 equals to see if values are the same, and they put a not and an equals to see if they're not the same. C will do the comparison between whatever the values are, doesn't matter what they are, whatever integer values they are, and it will put a 0 here if it is not true, and it will put a non-zero value, but not necessarily 1, if it is true. So when we go down here and we compute less, less, greater, equal, not equal. Right? Oops, not equal. Spelling. So you can see we did the computation of less, and it gave us a 1, which is what we expected because it is less. We computed the value of greater. It gave us a 0, which is what we expected because it is not, x is not greater. We checked for equal, also not true. We checked for not equal, and it is true, right? So now, that should be hopefully really easy to understand. It basically just produces a 0 or a not 0, depending on the circumstance. But let's see what happens, just so we're clear on everything, if we compared it y, let's say z and w, right? So we put some other values in here. There we go. Off we go. So now we compute less. And we say, is z less than w? Well, z is much higher than w, so obviously that's 0. Didn't happen. So now we say, is z greater than w, right? And it turns out that z is, in fact, greater than w. Still writes a 1 in there. Equals, right? They are not equal. Not equals, they are, in fact, not equal. And so basically, any values that you put in there, no matter what they are, will still produce a 0 or a not 0 value. Now, it is worth noting that the compiler, at least as far as I remember the spec, is under no particular obligation to actually produce a 1 there. I think it just has to produce some non-zero value. And I don't know if that's true or not. Check the spec. It may even differ between C and C++ for all I know, because in C++ they have an actual type called bool, and it may be that these things are defined to produce. I don't even know. I don't care at all about it. All I want to do is just make you aware that the compiler may not be required to actually produce a 1 there. It's just required to produce something that is not 0 if the thing was true. I know that for a fact, but check the spec if you want to know if it actually has to produce a 1. But anyway, we can do that for any variables that we want to. We can always compare them like that and then get back what we need. And those are called the logical operators, and that is what they look like. Now, why do we want those? The reason that we want those is so that we can do control flow, which is the next thing that I want to talk about. So control flow, the way that works, is basically saying, okay, I might have some code, and here is where maybe we'll bring our output debug string back into the mix, because I know everyone really loved output debug string. I know they were a fan of output debug string. They thought it was awesome. And so maybe I just want to do something like print out which one of these is greater. So I want to print out like z is less than w, right? Or I want to print out w is less than z, or I want to print out w is equal to z, right? I want to print those things out. And so what I have to do, obviously, if I'm to run this program, right, I run the program, and I print out all 3 of them, and that's not what I want. I want it only print the one of those that is true, because only one of them can be true. And so what I'm going to do is I'm going to introduce control flow. Control flow is a way of preventing code from running unless something is true, basically. And you have a lot of options to do that in C, and I'm going to show you the first and most basic one right now. So I am going to do this test. I'm going to say z is less than w. That is z less than w. And I'm going to say if that is true, then print this out. And so what you do is you start with the if, you open a parentheses and close a parentheses, and then you put the actual value you want to test in there. Now that value can actually just be a variable. So if I want to, I already computed it, right? I already computed z less than w. I can just go right on the variable. It's just a value. And I can put the expression in as well that could produce that value, and it will evaluate it here. So it's whatever you want. It just has to be something that evaluates to 0 or not 0, and then it's going to be able to do the thing in there. Now, if that wasn't true, now I can just leave it like that if I want to, right? I can make that be all that's going to happen, right? That could be the end of it. And now I could run that, and basically, oops, why I gotta get rid of my rebuild test. I want to get rid of these warnings. I'm sorry that there are some warnings in here. So this we'll just sort of expand our comment out to, there you go. So no warnings now. So I run this, and you'll notice it did not actually print out. It did not print out this thing. And why didn't it print it out? Well, because less, as we know, as we stepped in here before and saw, less is equal to 0. Now, if I want to, I'm going to print out this other thing. So I could, if I want to, I could also just do, well, let's do greater, right? I'm awful at this editor. It's true. I don't deny it. So this is z is greater than w. Run it, right? Unsurprisingly, we now get that because that is a value that we actually knew to be 1, right? And furthermore, I could also test for equals, right? I could see what the equal one is. In fact, I can do all of these, right? I can put them in here. Do. And done, right? So that is the way to make some conditional execution, and basically what happens is when we look at it in the actual debugger, you will note that any time the condition is not true, it just goes ahead and full-on skips everything that is within the curly braces. Those curly braces are called a block. We will talk about them in the mainstream more. But basically everything inside the block gets executed if the if statement evaluates to true or not 0. And everything everything inside gets skipped if it does not. And you can see that's exactly what happens, right? No big mystery there. Very, very straightforward. And what you will notice is if, for example, you already did a test on something, it is often the case that you may want to do the opposite thing as well. You may want to have some code that executes when it is not the case. And so instead of testing for not equal as well, equal is basically the same as testing for not equal because it's just the opposite case. So what C also allows you to do is at the end of your if, you can put an else statement, and the else statement can basically contain what to do when the thing fails. So when this is 0 instead of 1, it will do it, right? And what we get there is we get basically the same behavior of the program. It's just a more concise way of writing it. I don't have to check the separate value. It just goes, okay, it wasn't true, so execute the else clause, right? And that's basically a way of just saying, I'm going to execute one either way. Now you can stack these up if you would like to, as I started to write down here, but then I figured it would be better to explain them in a slightly different way. You can stack these up. So let's say I'm on here and I do if less. Well, I know that if it's less, then it can't be anything else. So I'm just going to put everything else in the else clause. I'm going to say, okay, well then I'll test for if it's greater, right? And then I'll test for if it's equal in here, right? I'm just going to do these tests. And I'm not going to bother testing if it's not equal to, because if it's not equal to it, it will have hit these things. It will hit one of those things because it'll either be greater than or less than. So we'll just do it this way for now, right? And when I run this particular program, you will note that it does exactly again what I said it would do. This is not true, so it will evaluate these. This is true, so it will evaluate that one. This is not true, so it will skip it, right? But if I know that these things are all mutually exclusive, so I only want to ever do one of them, I can actually stack the ifs inside the else as well, like right on the same line. And that will basically allow me to keep cascading ifs as long as I actually want to, like as many as I want to, like this, right? And even at the end, I can have a final pass-through else, which is like, I don't know what happened. Something went wrong. What? Right? And now when we run it, basically what happens is it will only pick one of these guys. It'll test them each, does that one. As soon as it finds one that's true, it stops evaluating any of the else's because they're all predicated on the fact that the previous one didn't occur. So that is the simplest kind of control flow. It's basically do something or don't do something based on the value of a variable. Now, that value, like I said, can be built up out of something extremely complicated, right? We could have done a ton of math here. We could have used all kinds of comparisons that got compared with each other and so on. But what we may want to do is test a couple things together, right? So let's say that we wanted to do, and this is basically just a glorified not equals test, but let's say we want to do something if less and greater were both true. Well, you know how we had those ors and ands that we used before, right? That used bitwise? We basically have the same ors and ands that we can use for logical. We can actually double if you just put 2 of the operator you're going to use, like logical or logical and, like that. We can actually do tests that test for multiple things at once. So this will do if it is less or greater, right? So when I run to this, it's going to actually look and see, how do I get this to go? There you go. It's going to look and see, this guy is 0, this guy is 1. He did an or, so he wants to do this case if either of these two things are true. And that is, one of them is true, so it goes ahead and does the case, right? And the same thing would happen with and, right? I can double the and it's saying logically, if both of these things are true, do what's inside, right? So it goes ahead and does that, right? One of them was true, one of them wasn't, which isn't an AND case, so it skips it and continues on. Now those are just operators like anything else, so I can again do them outside. I can make this an AND operator and take this guy out, right, like that, and then just test on the AND. Does that make sense? These are just operations. There's nothing magical happening inside the if. The if just wants a value. So we do all our computation outside with it. And there is even a logical XOR, I believe. I've almost never typed that in. But I believe you can even do this, right? If that makes sense. You can say, I want to do the thing, but I don't even remember if that's true. No, apparently it's not true. I would say I've never typed that in, but I was like, wonder if you can do a logical XOR. Apparently you can't. So never mind. Anyway, that is essentially all there is to predication and control and predicated execution in C. That's basically the if statement and the else statement are all you really need for that. Now it's worth noting that you don't actually need these little braces here if you only have one thing that you're going to execute. Meaning you might have seen in other languages you'll do something like this, and then you'll have the code just right here, right? And that is something you can do, but it's very misleading, I find, because there's a number of cases that include like macros and stuff, where like if, for example, the thing that's in here accidentally becomes two statements somehow, like you type a second one in there, it's really gonna look visually like these are only happening if the if is true, right? But really, C only does the very next thing as part of the if. So this being on the same line ends up being very misleading because it looks like it's going to be true. And so I always prefer to actually just really show what is going to happen by enclosing them in braces and making it a separate block so that it's obvious what happens in the if. And even with macro expansions and all kinds of other crazy stuff, this will always be a pretty solid, reliable visual indication of what's going to happen. Same is true on the else. If you want to, you can put the code right there. But I never do that. I always do that. And that is really just a personal preference, but I think it's a more solid and more reliable way to keep things from accidentally spiraling out of control if you happen to be using macros or other things like that. Okay, how is everyone doing on the stream is the question. This has been a crazy Sunday. We've just been going absolutely crazy. It's full on banana cakes, but you know, that's just how things go sometimes. Are we doing okay on the stream? Is everyone happy? I need to wait a little bit because the amount of time it takes before the stream actually gets on there. I guess that's true. So Clemens Baum did have a good point there. That was a good point. He basically pointed out that, well, yeah, there's no I was saying about XOR. There's no XOR operator like that, but it's true you don't really need it because this is essentially the XOR operator. Saying something is not equal to something else does effectively give you the XOR operator because that's what that is. So that's a good point. So why bother? Like, I mean, basically this would have just been C adding syntax that wasn't really necessary. So it's probably better that they just didn't bother, right? And you just know, well, if you wanted XOR, yeah, you can't type it to look like an XOR, but it is an XOR. That's what it is. That would explain why I've never typed this or never even thought that I needed it, because you just kind of know, like, okay, I can do that. B for binary watch. Okay, the stream has spoken. I'm hoping this is true. Let's see if that's true. Okay, Can we get a binary watch? Let's do it. Oh. All right, sorry, man. Thank you for the suggestion on binary watch. It doesn't look like it worked. That may be because we are still in Visual Studio 2008. Maybe when we switch to the thing, it'll work. But I don't know. Like I said, it might be a feature that they added. So yeah, that's good. All right, is the stream going okay? Everyone's okay on the stream. We're gonna assume that it's going okay. We'll try it. We'll try it on the 2013 when we go to the mainstream, and hopefully that'll work. So that'll be good. All right, so we're gonna keep going here because it's Sunday and we're just going nuts. We're just gonna go into the remaining control flow structures just so we can show you what they are. So sometimes, you know, before I wrote this thing out, I did a little thing where I'm like, hey guys, you know what? let's set this thing equal to OXA, and then let's just go ahead and shift that up by 4 all the time. Right? And then I showed, I went in here and I was like, okay, we've got this value. We look at it in hexadecimal. We can see the A. We shift it up. It's moving. There it's going. It's like it's going crazy. It's shifting, 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 and it's fun. But it is kind of annoying to have to write all this stuff. So if there is something that I want to do repeatedly, we have things called basically loops, if that makes sense. And loops are things that allow you to go through and repeat some code that you've written once so that you can do it multiple times. So if I want to do this a bunch of times, what I can do is I can basically say, well, let me do this until something is true. And that is called a while statement. You can say while, and then you can say something is true. So I'm going to say while x is not equal to 0, right? Because if x is equal to 0, that means we shifted the A all the way off the end. So while x is not equal to 0, I'm going to shift it. And I'm just going to keep on shifting it and shifting it and shifting it till it gets off the end, right? So if I run this, I go into my while loop. X is obviously not equal to 0 yet. So I go in here and I shift it, and you'll notice it just keeps on going, keeps on executing until we finally shift it all the way off, and now that's not true, and bam, I'm out, right? So a while loop is really trivial. It's just one conditional, and again, that can be a variable as well. So I could do, this is the condition, right? Right? And then I can say while condition. Now, it's only going to execute the code in the loop. So since condition was set up here, it would never recheck. So I would have to, again, set it. I would have to test it each time after as well, right? To keep re-upping it. But now you can see explicitly what's going on. Hello? Okay, there we go. You can see explicitly what's going on. Condition, I bring it up here, you can see is 1, because that is true. I go and I shift it up, and I reset condition. It's still true, still true, still true, still true as we shift. And then finally, this time through, I shift and it becomes 0, and now condition becomes 0, and I'm out, right? Loops are incredibly simple. That's all they are. The only other thing you really need to know about loops is that the loop can contain an escape. So if I was to do this, right? Basically, if we look at this, you'll see that there is no way to ever get out of this loop. Oops, sorry. Let's say while 1. That's just true, right? It's just full on true. So I'm going to do this, and it's just going to do it. And it's going to do it forever. And there's no way to ever get out of this loop, because 1 is a constant, and it's true, and it's not ever changing. So we just go and 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 go some more, right? So one thing that is true, though, is at any time we can actually just hand code, essentially, the escape from the loop by using what's called a break statement. So what I can do is I can put the conditional in here and say, oh, okay, well, if x equals 0, right, which is the time that I want to stop doing this loop, like I said, I can just put this break statement in. And what the break statement will do is it will jump straight out of the loop immediately, like right at that time, without doing anything else. So as I go through here, as I shift it up and up and up and up and up and up and up, right, when I get to the end and I'm about to shift it off the end, I get to the point where x equals 0, I'm there, I break out, and that's the end of the loop, and we're out, right? There are 2 more kinds of loops. You can actually, they're for convenience. You can write any loop with any other loop. There isn't like some kind of weird thing where like you have to use one kind of loop or the other because they do something differently. They are all basically just shorthand notation for essentially what is a conditional goto. It's basically saying when you get to the end, go back to the beginning. They're all just shorthand for doing that in different ways. There is a do while loop, which is basically you take the while and you put it at the end with a semicolon after it, and then you put a do at the front. And the only difference between those two is whether it executes the loop the first time. So for example, if I was here and I did x equals 0, right? So now I'm saying only do the loop when x is equal to 0. Well, what's going to happen? Well, we're never going to do the loop because x is equal to a, right? OXA. So it's not equal to 0, it's never going to do the loop. But maybe I wanted my loop to at least always run once. I didn't want it to check the first time. I always want to do at least one shift, but then I just want it to stop doing shifts when x finally does. I want to stop doing shifts if x was not equal to 0, right? Well, when I do this, that's exactly what happens. It'll do the shift, right, once, it'll get to the while, and then it'll end right there. So do is just a way of moving the test till after the first one. So if you want to always do at least one, that is where to do it. And again, it's just shorthand. It's just the same. I could do the exact same transformation using the while loop by saying, oh, it's really just while one, and then I do the if here, right, and the break. That's all I did, essentially. And so, oh, sorry, not equal to, right? So whatever the while condition would have been, I can just test the not of that while condition and do the break. So basically, these are all just shorthand. There's nothing particularly fancy to them. They're not particularly interesting. It's just different ways of writing the conditions. Finally, because it is very common, there's a thing called a for loop. And what a for loop does, oops, almost wrote it my standard way. What a for loop does is a for loop allows you to basically go ahead and move a variable's initialization, right, its test, and its operation all in to a single concise form that can be pretty easily read. And in this case, we don't even have anything to do in the body, but this is where, more stuff would happen here, right? If you were doing a more complex for loop. The for loop is basically kind of like the uber loop, the thing that packs the most into a small space. You can see what happens if I run here. It will actually do 3 different things separated by semicolons. This is the first one, and this happens once at the beginning. It has the conditional. This is the condition for the loop. So as long as this is true, it will keep going. And then it has the thing to do every iteration of the loop. So every time it repeats, it will do this thing here, right? So what happens is it goes and it does, oops, there's that conditional compilation. I don't know why it always wants to do it, but it always does. So I've got my x max equal to 0. First time through the loop, it sets x equal to xa, which is this line right here. The next thing it does is it does the test to see whether it should execute the loop, which is x not equal to 0, x is not equal to 0. So then it would do the body of the loop normally, but since we have no body, it's just going to go ahead and do the one thing that we told it to do every iteration. X equals x shifted up. It does the shift, right? End of the loop. Keeps going. Testing, 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 until it fails, right? And then it goes out. Now, it would be nice if the debugger actually showed it doing the test, but what it actually puts the little green, yellow arrow here on the test usually, which is kind of annoying because you'd rather see it actually pointing here and evaluating it, but yeah. So anyway, to make it a little more explicit, I'll put the output debug string that we were using. I'll go ahead and put that there so you can see when that executes in the grand scheme of things, right? So we're going to put the output debug string here and say we are in the loop. Okay, and here we go. So we go through, and our first time through, x gets initialized to a. It tests that it's not equal to 0. It's not. So now it's going to do output debug string, right? So it does output debug string, and, well, we don't have the, I got to actually put up the output window if we want to see this. But here we go. There it is. We are in the loop. It now goes and does the thing to do on each iteration at the end, which is to shift it up. It shifts it up. It now does output debug string, right? It now does the test. Again, shift up, test, shift up, keeps going, do, and then we're out. Oh, and we end up in, of course, Windows code, the C runtime library. All right, so that's about it for loops. They're not very interesting. For is the hardest one to understand out of them because it packs everything into here, and really these things essentially get expanded. So if you want, here is a more concise way of looking at what a for loop actually does. A for loop actually does, where did my int x go? Yeah. Anyway, so basically what this for loop exactly translates to is this while loop down here. It translates into this, if that makes sense. So these two things, minus obviously the part right here, although I can show you where that would happen as well. There you go. Now they're exactly equivalent. So basically the way these work is they're just kind of, they can all be transformed into each other. They're all exactly equivalent. They just have different sort of shapes and stuff to them. So basically what happens is a for loop that looks like this will basically just you'll do this thing. So there it is. It'll then do a while loop on this. And each time through the while loop, at the end of the while loop, before it does anything else, it'll do the thing that you put last here. And again, it's a little hard to see that in the debugger because the debugger kind of didn't really move the line thing to where it should have moved. But this is, conceptually, this is what the code actually is. So these two loops do substantively the exact same thing. It's just they're written in a different notation. And you may find one or the other more easy to read. Now, the reason a lot of people prefer for loops is because it's not really because they're more flexible or do anything really all that interesting over, like, say, just writing it as a while loop like this. Usually the reason they do it is because it makes it easier for people reading the code to see what the main sort of reason for the loop is. Because it puts out in it sort of the person who's the loop controller. The variable that's going to be tested and initialized and tested and changed typically goes in here. So it's just an easier way for people to see, oh, this is a loop that shifts X. I can see that's basically what this loop is doing. And then I know that everything in the body of the loop is just stuff that just has to happen on every one of those. That's like kind of stuff that happens with the X or whatever. So that is why people often prefer for loops, is because they give, you can see that these are kind of spread out and not really all that related in the code when you look at it here. It's not that obvious, especially if you imagine, you're typically looking at code that has like all this other crap sort of strewn all throughout it. And in that particular case, it gets pretty hard to see necessarily what the loop is. Whereas if, you look at it here, the for loop's going to have that stuff all sort of mixed like this, but the X is still, it's really clear what's happening here. Right, so it's pretty easy to kind of isolate it. So it's usually like a legibility concern, and that's mostly what a for is for. Okay, so that is pretty much it for flow control, except for one that I'm probably going to end up using in the stream a bunch, so I just want to mention it. If you're tired of writing if statements a lot, there's a thing called a switch statement. And what a switch statement is it's something that basically allows you to put many ifs together, assuming that they obey a couple quick rules. So if I have something like, okay, I've got some value, it's x, it's equal to 3, and I want to do something on like a ton of different, sort of things that x could be, right? X could be 0, x could be 1, x could be 2, whatever, right? So I've got all sorts of things. This editor, I do not get along with very well. Why are you doing these things? Okay. So I want to test a bunch of things, and basically, like, I kept doing this, and I wrote, the X test over and over and over and over and over and over again, right? And so what a switch statement really allows you to do most of the time these days, there's some other uses for it, but they're kind of a little janky, like Duff's device and these other sorts of weird things. But for the most part, what a switch statement is if you are going to compare a variable to a bunch of constants, you can put the variable or the expression, whatever, something that evaluates to a number. You can put a switch statement in, and then you can use what are called case labels. And these case labels basically just have the different values that you wanted. Case 1, case 2, case 3, case 4, case 5, and case 6. All right, so this has all the different ones, right, that I had here. Now, you'll notice there's actually a final thing that I could do here, right? I could put an else that was like, if none of these were true, it finally does this one thing over here, right? Oh, and of course I need to actually type the if. Don't want to forget that. Okay, so assuming you've got that set up, this tests them all, right? And it's going to do something here, 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 and here. And I want to write this a little more concisely. I can write this as a switch statement, and I can even do the final else. There's a thing called a default case, which is basically the case when none of the things are true. And what this basically does is the switch statement basically jumps to whichever one of these case labels is true. And if none of them are true, it jumps to the default, right? So it's basically just a more concise way of writing this. But it's important to remember that it only does the jump for you. Only the jump. So for example, if the thing that I was trying to do was this, right? This is what I've got. I'm going to print out so I've basically got all the cases here. I've got 6, 5, 4, 3, 2, and 1, right? And x is equal to 3, so we would expect to do our x equals 3 test. We'd expect to print that out, right? Well, if I go in here and do exactly the same thing with my switch statement, right? You can see it is definitely more concise. But if I do this and expect it to work, I will be in for a little bit of a surprise. So we run this code. Let's compile it first. Make sure we don't got any errors. Okay. So I jump in here. I got x equal to 3. I test it 0, it's not 0. I test it to 1, it's not 1. Test it to 2, it's not 2. I test it to 3, it is 3. It outputs 3. Ifs work just the way we thought they would, just the way I described them early in the stream. Everybody's happy. I come down to the switch statement. X, of course, I can look at x, it's still 3. Right, there it is. And if I do my switch jump, I jump right to case 3, and I'm super happy. It's going to print case 3. Everything's great. But what happens now? It prints case 4, it prints case 5, it prints case 6, and it prints the default case. What's going on? Well, the answer is, like I said, switch is just a jump. It just jumps to the case that it was supposed to do. It doesn't stop executing after it does the jump. So it'll just keep on keeping on. So again, you've got this break statement that I was talking about that exits loops. Break can also be used to break out of a switch. And what that does is it jumps out to after the controlling block of the switch, after the sort of the curly braces that enclosed the switch, right? So what I want to do is I want to put a break statement in each of these so that after it's done, it will actually go out. So now if I run my code, it'll do the same in both cases. It'll come through here, it'll execute the case 3, now it'll jump to case 3, execute, it'll jump out. So both of my things print case 3, which is what I wanted. Okay, so there you go. So it's pretty simple, the switch statement. And you can even use this to your advantage if you want to. Let's say you want to do something in case 1. Like let's say case 1 actually looked like this for some reason. Or actually I should say case 3, because that's what we're on right now. So let's say case 3 actually also did the stuff from case 4, right? Well, if that was the case, I could just eliminate this break, and now we're good to go. Oftentimes people will put a comment in here so that you know that it was intentional. This falls through, because it is kind of common for people to forget to put the break statement in as a bug. And so you kind of typically want to let people know. But in that case, you get sort of the drop through for free. So here we go. We do 3 and 4. We jump in, produce 3, produce 4, and then we break out. Right. So that's what you would expect. So that is the switch statement. Okay. Final thing I want to talk about on this stream, I think. And this is going to be the last stream since the main cast. So there's a couple of things I didn't get to. I didn't really get to dereference operator, which is, we sort of kind of did it a little bit, but not much. And I didn't get to to's complement. So maybe we'll try to do them in the Q&A. I don't know. We'll see. But in the main stream, I think in this stream, maybe we're going to wrap it up soon. The last thing I want to talk about is I haven't really discussed blocks outright. I just kind of introduced them at the beginning and kind of showed you them here. We did a bunch of them with the loop bodies and stuff, and you've seen all these curly braces, but I never really outright said what goes on with a block. And the answer is a block is basically a logical part of the program that does have flow control implications usually if there's something preceding it, like an if. Because like with an if, this logical block here doesn't get executed if the if isn't true. So oftentimes there's an attached piece of control flow, or like a function, right? This is an attached piece of control flow that says this block only occurs when this function is called. So blocks encapsulate code, they sort of bundle it up in a way that it only gets run if a particular piece of code control flow is true, but they have some other properties. One is that variables declared inside them, right? And I'm going to go ahead and actually vape all this right now. Goodbye. Variables declared inside them. So if I say int y equals 5, and then I open a block, because I don't even have to put control flow there, but I could. Let's say it this way, if y equals 5. Variables declared inside them do not exist outside it, right? So if I do this, I will get a big old nasty error. And basically what it says is x is an undeclared identifier. Well, what do you mean? I declared it right here. Well, no, you didn't, because a block basically captures all of its variables for only itself. Nothing can come outside of this. Nested blocks, blocks that are inside, can reference x just fine, right? That's fine. So anything that I do in an outside block will totally work, but, oh, well, of course I gotta delete this guy first. That will totally work, and that's fine. But things outside, if that block occurs somewhere else outside in the program, that is an error, and that's no good. So yeah, so there you go. And again, the indentation doesn't actually matter here. That indentation is just syntactic. It's not syntactic sugar. It's just formatting that is C programmers use so they can see what's inside what block. But it's really only the blocks that matter. So for example, I could easily just write the code like this if I wanted to for some reason. That could just be my code. It doesn't matter where it's not like Python where you have to have indents in a certain way or anything like that. It doesn't care at all. It's fine. So what happens with blocks is they're basically like the stack thing that I was talking about before, where I was saying that's where variables live and they get pushed on the stack and then pulled off the stack. Well, you can basically think of blocks as sort of being having their own sort of stack implication. When I enter a block, by the time that I get into that block and start doing stuff, it is incumbent upon the compiler to have pushed the space, to have made space on the stack for these variables that are in the block. So if I start doing stuff with variables in this block, by the time I start executing code in there or doing whatever, this stuff needs to be on the stack and live, and I can do stuff with it. But once I get to the end, it is no longer incumbent upon the compiler or the operating system to keep those things valid. So as soon as you exit a block, it is entirely legal for the stuff that you were working with to just disappear, right? It can just be gone. Now, oftentimes it's not actually gone because you could still access it because it's still, the memory is still there and hasn't gotten like overwritten or trashed or anything yet. But if you were to use it, that would be a big source of potential bugs because the compiler is no longer under any restriction to keep that space used for what you told it to be, so it could just go use it for something else, and then you've got a bad bug because you're trying to use something. Now, you may ask me, well, Casey, you just said that you can't refer to it. I just saw you, right, basically do this, okay? And when you did it, you couldn't even compile the program. So the question is, what are you talking about? What do you mean I could reference it? Well, remember, C allows you to do a lot of direct stuff with memory. So maybe I define a pointer, right? And that pointer doesn't point to anything at first, but in here, this pointer equals the address of X, right? Well, now, when I get out here, I can actually do stuff with that. Oh, and hey, this gives me an opportunity to talk about that. Dereference operator, actually. Ooh, this is going to be good. This is going to be good. This is a good Sunday stream. We'll talk about that in 1 second. So if I were to take the address of X, like we've been doing for this whole stream, where I just take the address where in memory X is, this pointer was declared in the outer scope. These blocks typically are often referred to as scope. It's like basically where you can, where variables are valid to reference and where they're not is often called scope. I don't actually know why, but it often is. So, but anyway, it's declared in the outer block. This pointer is declared in the outer block, which means I can reference it anywhere in the outer block, right? So if I want to, I can snap the address of X. I can find out what the address of X is while I'm in this scope. When I get out of the scope, when I get out of the block, X goes away potentially, but I've still got its address. So I can go ahead and write to it all I want, right? And so when I go ahead and compile this, it compiles just fine, right? And what happens is, when I go in here, you will see, I will take the address of X, right? And now I know where X is. I know exactly where X is because wherever it was pointed to, right? That is the actual value of X. It was set to 6. It's still set to 6, right? Even though the compiler is not under any obligation to keep that space available, it can use it for something else. I can write to it and bam, I just wrote to X even though it's out of the scope. Totally not, you should never do it. It's just asking for disaster. But like I said, everything in C is just happening in the memory. It's direct there. You can go to town on it. And if you want to create bad bugs waiting to happen for yourself, you can. So I just wanted to kind of underscore the fact that this is sort of stuff that helps to protect you. This sort of scoping where you wrap variables inside scopes and then they go out of scope is to help you not make mistakes. And when you're doing stuff like this, you're basically just asking for trouble. There's almost never any reason to do what I am showing you here, but the point is it is possible because it's all about memory, and this got some memory at some point, and that memory hasn't been freed yet or marked as inaccessible by the operating system, so we can just keep on writing to it and it works. So the thing that I wasn't going to cover today, it turns out that I am because I just used it to show you something super naughty, is this star. So like I said, star is normally math. If I do x times y, right, that just means multiplication. So if I do, y equals x times y, I want to do x times y and I want to assign it to y. That's all fine, right? But the star has another meaning when it appears as just a prefix. So when it isn't x times pointer, if it's just pointer, right? And I can even wrap it in parentheses to make sure that even if there was an x out here, it wasn't going to do anything or whatever, right? So I've got, this thing. What that means is I'm talking about the thing that this points to. It's a pointer, so I want you to do the operation as if you had the thing it was pointing to here. So this is pointing to x, and I want to operate on x, so that turns it into x, essentially. It turns it into the memory location that x was, right? So basically, if I have int star pointer, and then I refer to star pointer, it's essentially the same as taking the declaration of what star pointer was, removing the star from it, and then whatever that is what you have left. So in this case, it's an int. So star pointer is the int at the address contained in pointer, right? So if I took an address of an int and stick it in pointer, which is what I did, I took the address of x, then from then on, star pointer refers to what's in that location. And so for example, if I wanted to get it out, right? So I do this, right? I want to know what was in x. Well, I can't refer to x because it's out of the scope. The block, we left that block, it's gone. Well, I can still just go ahead and get it, and I can put it in y because y, right, is set to 5 right now, but x was set to 6. Bam, I just accessed it. There's its 6. And so all that's doing is basically the stack. It's just going into the stack into a location that's not supposed to be used anymore, but I know the value's still in there. I know it's in there because the program hasn't done anything else, right? So I know it's still in there, so I just grabbed it out, and I can do that. That's totally legal. And the dereference operator can get nuts if you want to, right? I could do something that's like a pointer to a pointer, right? It's a pointer. And I can take that and make the pointer be equal to the address of the pointer. So now I'm pointing to the pointer that's pointing to x, right? And I can go ahead and get it out that way. I can dereference it twice, right? Again, full banana cakes for a Sunday stream? Why not? Bam, got it out. And so the dereference operator basically chases the pointer. It says, go to where this pointer points, and I'm talking about that now. And if I do that and I want to do it again, I can just go, okay, that thing you were pointing to, that's a pointer, so go find what that was pointing to. And it all just works, right? So you can do that. You can have as many as you want. You can have pointers to pointers to pointers to pointers. You can have pointers to structs with pointers in them that point to other structs that have more pointers in them, and you can chase them all day long. That's how you build data structures often. Linked lists are pointers that point to structs that have pointers that point to the next one, that point to the next one, that point to the next one, that point to the next one. You want to walk the list, you go through all the pointers. Just point, right? So that syntax that I used in a previous stream, right, where I had a struct and I said, oh, there was a pointer and I referenced some member of the struct, essentially that is just the same as dereferencing the pointer, the way that I just showed you how to do it, and then putting the dot. And so another way to look at that whole dot arrow thing that I was saying, is like it's kind of janky, is basically like the arrow is sort of like saying dereference the pointer first, then do the dot thing. If that makes sense. So there you go. Last thing. When you open a new scope, you can shadow a variable. And I snuck it in here, but I don't know if anyone caught it. There's some eagle eyes on the stream, so I assume that they probably did. But basically, what happens is, if you have two variables called y, normally that'd be an error, right? Normally, if I did this, that's not going to compile. It says you have redefinitions of y. But you can always shadow a variable by declaring a new one in a scope inside the outer scope. So if I make a new block inside an old block, that block can define y again, and it's a different y. What if you didn't know it was a different y? I just told you how you could determine that, actually, right? Let's do it. Here is y pointer 0, and here is y pointer 1. Let's go ahead and make y pointer 0 equal to the address of this y, and we'll make y pointer 1 equal to the address of this y. Now, if they were the same, that means they're the same y. If they're different, that means they're pointing to different memory locations, so they're different y, right? Because it's all about memory. If these things are in different places, they're not the same y. They're just two names that point to different memory locations that just happen to both be y. Well, let's see what they are. So what do we got? Y pointer 0, y pointer 1. Different, right? Not the same value. FAE4, FAB4, and that's how you know that they are actually in different places. So this made a new y. And that is the only time it is legal to do that shadowing. You have to open a new block. Like I said, you can't shadow a variable by declaring a new y in the same block as someone already declared a y, right? That's not allowed. So let me look over my list really briefly here. Is there anything else I want to go over? I think I'm going to skip 2's complement. Sorry, guys. Looks like I got just about everything. So I think that is it for our test streaming. It has been very productive. This was a crazy Sunday stream. I am going to stop the stream now, and we are going to go on to the Q&A in a second here. But first, let me say thank you so much, everyone, for showing up. We've had so many people on the stream. We had 300 people today, almost 400 at one point, it looked like, too. That's a lot of people watching the stream. So thank you so much for helping me test out the streaming. I think it's going to make a huge difference when we actually start the proper stream on Monday, having me practice doing this, but B, we've also had like a ton of people who have, sort of written in and told me things to do that were really beneficial. Like, for example, stuff that I need to set on Twitch and how to, like making the font size bigger, all that sort of stuff would have been stuff we'd have to work out in the middle of the mainstream, and we've gotten a lot of that stuff sort of squared away now, which makes a huge, huge difference, I think, when we actually start on Monday. So thank you, everyone, for all that help. I will see you in the Q&A if you are interested, and if not, I will see you on Monday for the very first actual game coding stream, which I think will be a lot of fun. So thanks, everyone, for joining us, and I will see you in a second.